We're Reese Levine from University of Santa Cruz is going to talk to us about testing Vulkan memory model.
Yeah, thank you very much. Yeah, so like I said, I'll be talking about our work on testing the Vulkan memory model and a little bit about myself. I'm a PhD candidate at UC Santa Cruz. I'm in my 4th year there, working with Tyler Sorensen, who unfortunately just had to leave to go back to Santa Cruz to teach a class. But hopefully I can answer any questions that you have about any of our work. All right, so I don't need to tell everyone here, there's a large diversity of GPUs out there made by a lot of different vendors, and frameworks like Vulkan are supposed to cover all of those GPUs, except of course Apple, but we do have Molten VK, so things kind of work there too. Now, Vulkan is both a graphics and compute framework, and I guess all of our work at Santa Cruz, or most of our work, has been on the compute side. So there's some motivation there. I mean, obviously machine learning has become a lot bigger in recent years. So there are frameworks like TensorFlow and PyTorch, and even this new one that we found that actually does have a Vulkan backend machine learning compilation. It does like LLM inference. So we're using compute workloads for a lot of different purposes. Otherwise, other kind of applications, high performance computing, your data centers do a lot of compute workloads, and then also on your edge devices. So this is a die photo from a recent Apple GPU, and the GPU takes up a lot of space on these dies, and they're used for a lot of different kind of workloads, and that kind of motivates why we're interested in a lot of this compute side testing of things. One of the kind of follow-ons when you start writing these general purpose GPU applications is you might want to start writing applications that synchronize. And by synchronize, I don't mean what every other talk today or the last few days has been about synchronization. This is more on-device synchronization. So for example, mutexes or locks or an algorithm like prefix scan, which I'll talk a little bit more about later, are both written about in the CUDA by example book, how you might implement those on NVIDIA GPUs. But there are also implementations in other GPU languages as well. And Vulkan is what we're interested in here today. Beyond those, there's also things like concurrent queues, which I know is used in Unreal Engine right now for some use cases, which requires synchronizing between threads on the GPU. And then maybe not as relevant for like Vulkan specifically, but research that we're potentially interested in later on is how you might synchronize even across devices using like NVIDIA's NVLink or the upcoming CXL technologies. And that's kind of where our work comes in, which is actually testing these foundations of fine-grained synchronization on device. So we actually have a demo that you can play with, and I'm going to go through this in a little bit, and it'd be great if people could follow along if they happen to have a device that runs web GPU. So that is today pretty much every desktop or laptop if you have Chrome on it. And I guess, yeah, Android, it's now available. So if you have an Android device, you can actually run our tests as well. And I'll keep this QR code up on the screen, and we'll go through some examples in a little bit. So what do I mean by the foundations of fine-grained synchronization? I'm talking about memory models, or memory consistency specifications, as we call them in our papers. And it's how we actually reason about programs that synchronize or access common memory locations. So this program right here is an example of a message passing litmus test. Use these little litmus tests to kind of show how memory consistency works and what kind of behaviors are possible. And this message passing test is actually the same pattern that you might find if you actually wrote a mutex or a lock implementation. So you have 2 memory locations, X and Y. You have 2 threads. Thread 0 writes 1 to both X and Y. This is using the relaxed atomic kind of notation that you might find in C++ or Vulkan, SPIR-V. And then you have a second thread, which just reads the values Y and X in reverse order that they're written. So you can think of X as here the data, and Y would be kind of the flag. So if you read the flag, you should be able to read the data. So let's look at what kind of behaviors are possible for this little test. So a common memory model or memory consistency specification that we might all be familiar with is called sequential consistency, where all events have a total order, and that order respects per thread program order. So what that might look like in a few different schedules is that maybe thread 0 runs entirely first, and then thread 1 runs. And when that happens, you get this outcome where both the registers R0 and R1 are 1. And we could just reverse that and have thread 1 run first and then thread 0. And of course, in this case, we get both outcomes, both registers equal to 0. So we can get slightly more complex schedules too. So for example, we could have event A occur, and then C, and then B, and then D. And in this case, because the read of Y occurs before the write of Y, it returns 0. because the read of X occurs after the write of X, it returns 1. So we get R0 equals 0 and R1 equals 1. And it turns out there's actually quite a number of other schedules, even for this little test, that give you that same outcome. The important thing to note here is that A and B and C and D retain their order. They're both in the per thread program order in all these schedules. All right, so let's actually go try it out. So if you haven't yet had a chance and you have a device that this might work on, you can head to GPU Harbor or scan this QR code. I'll leave it up in 5, 4, 3. Okay, move on. And I can't run it on this computer, but I did take a video of what this looks like. So when you get to GPU Harbor, you can go ahead and click on the Web GPU memory model testing page, and then go over to the left here and click on the message passing tab, which shows that we're going to run this exact same test, and we're actually going to run it on your GPU, or my GPU in this case, on using the Web GPU framework, which of course may go through Vulkan, depending on what your backend actually is. So I'll pause it right here really quick so you can see this is the outcome. If I just run that test, I run it with some number of threads, and they all kind of do this kind of 2-thread message pathing test. And you can see I see a bunch of outcomes here where both R0 and R1 are 1. And then I see, a few hundred outcomes where you get that interleaving of thread actions. Has anyone else managed to run it? And did you get something similar or any other outcomes out there? Similar. Okay, cool. Yeah. So that's interesting. I guess we see some of these outcomes and we're like, all right, is that what the GPU does? Like, is that the only possible outcomes this GPU has? Well, it turns out through our research, we've done a bunch of work on this and figured out that the actual behaviors of these tests are very sensitive to the environment in which they run under. You can imagine you're running other applications. If you have a bunch of other threads doing other sorts of work, things can change. So we have a setting over here on the right that we call the stress setting. It's kind of a default that works well on laptops, might not work so well on phones, might be a little slow. But if I just change it to that and run it, you can see that my behavior profile here changes a lot. So now we get a lot more outcomes, so millions of those sequential outcomes, a couple thousand of those interleaved outcomes. And then we see this other red outcome where R0 equals 1 and R1 equals 0 that I haven't really talked about yet. So if you run it, maybe you saw this, maybe you saw something a lot different. Maybe you didn't see those weak behaviors that I'm seeing here or this red outcome, which I'll talk about in a second. But I think the takeaway from this is, one, to realize that different devices are going to have a lot of different behavior profiles. Like, just because my device showed this type of behavior, your device might not. And also that the actual behavior outcome is going to be a lot different depending on whether or not you're running it under this stressful environment or not. So that's kind of the interesting thing around looking at these results. Now I will go back to the slides, and let's actually take a look and see what that extra result is that we hadn't talked about yet. So if you remember, it was R0 equals 1 and R1 equals 0. So to make that happen, we know that the read of Y in event C has to read the write from event B. So we just say, okay, let's try and put B before C. And then let's say we're trying to maintain sequential consistency. Then we know that event D has to occur after C to maintain that per thread program order. But now for this read of X and D to return 0, we know that the write has to come after it in some sense. So A has to come after D, and that's how we might get this outcome. Of course, there's a problem here in that A and B are flipped. So they're no longer maintaining that order. Okay, we could try and fix that by just giving them their order, A and B. Again, we know that C has to occur after B. But again, for that read of X to return 0, we know that D has to occur before A. So now A and B are in order, but C and D have been flipped. So yeah, there's a problem here. So what does this actually mean is that modern devices, CPUs and GPUs, implement relaxed memory models that allow these sort of weak behaviors that can't occur under sequential consistency. And what those actually correspond to in your hardware or your compilers is optimizations. Like we've decided that for our processors to run fast enough for what we want them to use them for, we have to allow these behaviors, and they can correspond to different kind of compiler or hardware optimizations to allow that to happen. So yeah, these are kind of unintuitive behaviors. Here's some other results from other machines, since you probably didn't see it on your own device. This is an Apple M2. You can see that without any sort of stress, we were still able to see weak behaviors on that GPU. And then with stress, you saw about 2x the rate of weak behaviors, but the profile doesn't change quite as much as on the device that I ran on, which actually was an Intel GPU. Here's some other results, some NVIDIA results. So you can see that there's even more kind of like extremely different between the without stress and stress versions. Without stress, you saw almost no behaviors besides that kind of sequentially consistent behavior. And then you see some weak behaviors with that kind of default stress setting. But yeah, again, the takeaway here is that you need stress in a lot of scenarios to actually see these weak behaviors, and that the profiles of these behaviors vary a lot depending on what device you're running on and what vendor that is. So a kind of natural follow-on to that is, what if we actually want to disallow these weak behaviors? If we're writing a lock, we probably don't want to allow this kind of stuff to happen because it could allow things to leak beyond critical sections. So here's that exact same program, but in this case, I have fences between the writes on thread 0 and the reads on thread 1. And specifically, I have a release fence on thread 0 and a acquire fence on thread 1. And it turns out that adding this sort of fence synchronization disallows the weak behavior if your memory model supports it. Vulkan, thankfully, does support it. It does allow you to write these release acquire fences to disallow these behaviors. But there's two questions that come from that. And one is, let's say you are an actual vendor implementing an architecture or implementing compilers, and you want to know whether or not you've implemented the memory model correctly. You might want to run tests like this. But what we saw is if you just run this test, even without fences, you might not see weak behaviors if you don't have the correct stress settings. So to know that your tests are actually doing something, you need to evaluate whether or not you're running your tests in a scenario that's actually going to cause these behaviors to occur. And then you could know that if you mistranslate, if you had a bad implementation of a fence or your architecture had some sort of bug in its implementation, you'd be able to find that by running this test. And the second question here is, if you're writing an application and you're relying on these fences to give you the behavior that you want, and you happen to test it on a system that doesn't show weak behaviors very often, you might kind of conclude, okay, my program is correct, and then you go run it on some other system and all of a sudden it fails because you forgot a fence. So when we're writing portable programs, we need to actually make sure that we're testing them on systems that are going to reveal bugs that occur in our programs. And yeah, how do we even know that's the case? So that is kind of the motivation for a lot of our work. So yeah, that was a long introduction, but I'm going to spend a decent amount the rest of the talk talking about kind of our work on this, which is portable testing in our two papers, MC Mutants and GPU Harbor. And then after that, I'm going to go briefly and talk about why memory models are actually not all we need to write applications that are interesting. And then I'm going to use a prefix scan algorithm as a kind of case study for putting that all together. So yeah, we have two papers that were both published last year. There are some of the authors in this audience. My co-author Devin is here, and then Reese Levine from Google is here as well. MC Mutants was in AskLoss, where it actually won distinguished paper, which was nice to see that other people in academia like the work we're doing on GPU memory model testing. And then we had a paper, follow-up paper, GPU Harbor and ISTA, which is a testing conference last year as well. And they both won distinguished artifacts because our website's kind of nice, and you can actually, WebGPU really helps us run a lot of these tests in ways that we couldn't without that kind of interface. So what was MC Mutants? It was basically a paper that developed a way to evaluate the effectiveness of MCS testing, as well as we developed some new testing techniques in the paper. So for example, if you look at this test at the top, which has those release acquire fences and should be disallowed by the memory model, we showed that if you are able to reveal this weak behavior in this bottom test with those fences removed, you should probably be able to find bugs in the top test. And we also look at this from a kind of formal perspective using axiomatic memory models, as a lot of people in industry and academia like to use to look at these sorts of programs. And we evaluated our methodology, this methodology, on 4 different GPUs, using WebGPU and using that website that I showed you. I don't think any of the backends in this paper were Vulkan, but coming up the following paper, we did test a bunch of Vulkan backends as well. Impact, we actually discovered several bugs. So we discovered an actual bug in AMD compilers where they were just mistranslating their fences. So if you tried to use release acquire fences on AMD GPUs, it wasn't working correctly. And so they fixed that bug. We also found a kind of coherency issue on Intel GPUs that were running on MacBooks, which we reported to Apple. That was similar to this test, but uses 1 memory location instead of 2. And then something that I think is really interesting from a Vulkan perspective is that we actually integrated all our tests that we ran into the official WebGPU conformance test suite. So now when WebGPU is being released or developed and they run their CTS, they'll actually run some of these memory model tests on whatever devices they're running on to test whether or not WebGPU implements the memory model correctly, whether or not the drivers and stuff underneath implement the memory model correctly. And I think that would be something that'd be really cool to get into the Vulkan CTS at some point too. So yeah, on MC mutants, we only evaluated on 4 different GPUs. So we had this follow-up paper, GPU Harbor, where we kind of scaled the approach of MC mutants. So we started with the kind of insight that our website, and we also built an Android app, allows non-experts to run the tests. So we kind of farmed out our website to friends and family and made them run it on all the GPUs that they had access to. And we actually ended up collecting data from around 106, well, exactly 106 different GPUs. Most of them are web GPU, which is a variety of backends, whether or not that's Metal or Direct3D or Vulkan. Some of those are like Linux Vulkan backends. And then we also tested 8 Android devices using our Android app. So overall, we got results from a lot of different vendors and a lot of different GPUs. And yeah, kind of an interesting stat there is we ran like almost 400 billion iterations of our tests and for a total runtime of around 31 hours, which is actually not that high if you look at kind of previous papers on memory model testing. And then something else which I won't really have time to go over in this presentation is we did this similarity analysis across all these GPUs around their weak memory model behavior, and that has impacts on how you might choose which devices to run on when you're running a CTS, because you couldn't obviously run it on the hundreds, necessarily run it all the time on all the hundreds of devices that we're trying to target with frameworks like WebGPU and Vulkan. But yeah, here's a kind of an interesting kind of results slide from the GPU Harbor paper, which looks at the different weak behaviors that are possible with different types of 2-thread 2-instruction tests. So we looked at that message passing test earlier, which is basically the pattern that you might find in locks. There's some other tests here. For example, the store buffer test is the classic kind of x86 TSO weak behavior that x86 architectures allow. And then there's other kind of combinations of reads and writes here that lead to different sorts of these weak behaviors that don't correspond to sequentially consistent behaviors. So some interesting kind of insights here, right, is that Intel GPUs on average seem to have relatively low rates of weak behavior compared to, for example, the Apple GPUs, the M-series GPUs, and NVIDIA is kind of in the middle, and then AMD had this really high rate of, on average, of store buffering behaviors on our web GPU results. And then if you look at our Android results over here, maybe not too surprising, but basically as you get larger Qualcomm Adreno devices, you start seeing higher rates of weak behavior. So definitely the size of your GPU makes a big difference on how often these types of behaviors occur. But also, we didn't really see a lot of weak behaviors on a lot of other of our Android devices. Like the Mali G71 and G78 did show this message passing behavior, but actually no other types of weak behaviors. We have an Imagination device here that didn't really show any, and then an NVIDIA Tegra mobile device that showed a few weak behaviors, but not too many. So again, coming back to this kind of graph has implications both for people who are writing compilers and hardware, because you want to know if you're testing your hardware, how you should test it, and this kind of gives you insight into like what sorts of tests to run. I want to be clear that all of these behaviors are allowed by the memory model, but if combinations of fences with these sorts of tests, you suddenly start running into bugs. And then the other thing is, yeah, if you're a developer and you're testing your code that uses fences and stuff on an Adreno 610, you're not probably going to be testing it to the full extent that you might need to. You probably want to run it on some of those bigger devices, and maybe just don't test it only on Intel devices. Test it on some other sorts of vendors as well, so that you actually know that your applications are going to be portable. So yeah, from this study, we found more bugs, and they actually all turned out to be coherency bugs, which is quite surprising because coherency seems to be a little bit simpler in some ways than memory consistency across memory locations. But basically all we did is we have this kind of test on the right here where we write to this one memory location X, we write 1 and 2 in one thread, and in a second thread, we just read that memory location twice. And a weak behavior or incoherent behavior here occurs when R0 is greater than R1. That shouldn't really be possible under the Vulkan memory model or the WebGPU memory model. But we observed it. We observed it on the Mali G71 and G78 GPUs, which is the GPU in the Pixel 6. So that turned out to be a compiler bug in ARM's stack, which they fixed. We also observed it on NVIDIA devices on the Tegra X1 and a Quadro P620. This turned out to be a Vulkan compiler bug, an NVIDIA Vulkan compiler bug, affecting all pre-Volta architecture GPUs. So we talked to someone at NVIDIA and they fixed that. And then we also observed, again, the same issue on GPUs from NVIDIA, Intel, and AMD, all on MacBooks running under Apple's Metal framework with WebGPU on top of that. And this has been reported to Apple. So yeah, that is kind of a very brief introduction to our work on testing the memory model of WebGPU and Vulkan and our papers on that. And with my last kind of 5 to 10 minutes, I'm going to go into why memory models are not actually all that we need and a little case study on prefix scan. So here's kind of an interesting program that you might want to run on a GPU. This is basically two threads contending for a lock in some way. Here they're just basically just trying to do like a compare exchange on a memory location M, and then then release it, and you could have a critical section inside of that, and that's how you might implement a lock. It turns out that GPUs in general are not fair schedulers. So my advisor, Tyler Sorensen, and some others wrote a paper in 2021 where they kind of ran this type of test and other types of tests and showed that in a lot of cases, GPUs will just kind of deadlock in this sort of scenario, depending on what order the threads are scheduled in or other sorts of kind of things that happen around the scheduling of threads. So yeah, they're not fair schedulers. And I think some of the interesting work that we want to do with Vulkan is to provide some guarantees on when they are fair schedulers and how we actually can write programs like this and not deadlock our machines. Now, beyond that, there's other sorts of interesting kind of fairness problems. So if you look at the C++ standard, it has this sentence that says the implementation should make atomic stores visible to atomic loads, and atomic loads should observe atomic stores within a reasonable amount of time. And that's as far as it goes. It doesn't tell you what reasonable means. And so when we're running locks on our CPU, we're all just kind of hoping that the architectures have chosen a small value for reasonable. That is, yeah, still a very ambiguous part of these types of specs that I think we probably want to improve upon. Vulkan does go a little bit further than I think previous GPU languages have gone and other GPU languages currently go by including things like availability and visibility operations, which should provide you some sort of control over how your memory kind of propagates out to other threads. But there's still interesting kind of problems here. And one that I think might have been brought up a little bit earlier is a few years ago, we were working on some code, and we basically ran into this issue where we had an infinite, we had a loop that should have been infinite, and basically that a compiler was optimizing out that loop because it thought it was infinite and running to completion, which we believe was not to be the case. And so here's a similar kind of, here's like kind of a very related piece of code that shows why that might happen, is that if you're doing a relaxed atomic load, some compilers might decide to hoist that relaxed atomic load outside of the loop and then spin on a temporary register. And of course, if your atomic variable here is now being written to by some other thread, you're never going to see it in your temporary variable. And so you're actually going to have an infinite loop here when it maybe shouldn't occur. And this pattern is actually kind of a nice little optimization that you might write when actually writing a lock where you spin on a relaxed atomic as opposed to spinning on an acquire atomic or something more kind of heavyweight. And yeah, so there was this bug where basically Mesa assumed that if you wrote this loop, it was actually an infinite loop and just got rid of your loop entirely. And so that was kind of a problem. And I think it ended up being fixed so that it doesn't do that now, which is nice. But I actually do know of at least one other implementation today that still does this. So there are still kind of problems around these sorts of relaxed atomics and forward progress things. And yeah, we need to do more work on testing them and putting more concrete language in specifications. Yeah, so that's a little bit on fairness and forward progress. So putting that all together, we can look at this prefix scan algorithm. So prefix scan is a general algorithm. One example of it is prefix sum, which is this little box on the top left here, where you have, let's say, an array of 1, 2, 3, 4, and you just compute a prefix sum of that. So you end up with the values 1, 3, 6, and 10. It turns out this algorithm is very useful. I know Rafe is in the audience and he uses it for a lot of different applications. And there's a paper from NVIDIA in 2016, which shows how prefix sum and prefix scan can be optimized on GPUs. But it does require both release acquire atomics across work groups, and it requires forward progress guarantees around, making sure that work groups will make progress. And that if you have a work group that's waiting on a previous work group, that it will actually, the previous work group will get scheduled to completion so that you actually make progress on your algorithm. And the goal with this sort of application is to basically match the performance of a memcopy kernel. You should really be able to, with this decoupled look back, prefix single pass prefix scan algorithm match the performance of a memcopy kernel. So I actually tried implementing this in Vulkan. I know others have as well. This is just kind of my toy implementation I did over the last weeks and months, and I ran into a lot of issues. One is that maybe it's just the drivers I was using, but I found that subgroup APIs are not super stable. I've run into seg faults. I've run into kind of very quirks of the kind of subgroup API for implementing these types of algorithms. I've also run into some weird driver issues that I'm not sure if it's my code or memory model bugs, or maybe I just need to update my drivers where I'm not seeing like work group memory being kind of propagated in the ways that I think it should. And then of course, Vulkan still doesn't have any forward progress guarantees. So all the code I'm writing here is technically not supported by the specification. So if we want to write algorithms like this, there's still a lot of work to go. Eventually, I did manage to get this algorithm running on one GPU. It was an Intel integrated GPU. And I did a 1 GB of data kind of prefix sum, compared that to a memcopy. You can see here that on the memcopy, I was getting around 33 GB per second. The prefix sum was giving me only about 24 and a half, which is like 75-80%. So I know it should be able to do better. I have kind of ideas around what I can do better in my code, but I also know that the code I'm writing should theoretically match performance of like the NVIDIA single pass prefix scan. So there's still work to do to make these sort of algorithms portable across different GPUs as well. Yeah, so I think that leads into some of the takeaways and discussion that I want to get out of this conference and talking to people here, which I already have somewhat, but it'd be great to talk to more people. One is that from our research perspective, stress testing techniques are necessary for GPUs, especially when dealing with things like the memory model, and how to evaluate this kind of stress testing techniques. I want to know what other people's use cases are for synchronization. Again, here I mean like within device synchronization, so having multiple threads coordinate, and what kind of use cases you might have for where your GPU needs forward progress guarantees across threads. I've talked about the memory model and forward progress, but are there other features of GPUs that kind of interact with these in ways that we haven't thought of and might require more research? And then I know that Rafe, for example, has an implementation of prefix scan that doesn't actually really rely on release acquire atomics to do it. It relies on kind of bit packing and relaxed atomics. And so there's kind of a question, like we have this very complicated memory consistency model, but is it really necessary in all cases? Like, should we be thinking more about simplifying it? And do real applications always need these sorts of guarantees? Yeah, so those are some of the takeaways. That was my talk on testing the Vulkan memory model. I showed an example prefix scan, but specifications are ultimately motivated by your use cases. So we want to hear kind of what else we should be working on in testing. And feel free to play around with GPU Harbor. It's got a lot of cool tests and interesting results. Or if you want to talk to me more after this, you can find contact info on my website. Yeah, thank you.
All right, thanks a lot. Interest of time, let's keep this to just a couple questions if we could. People have questions in the audience?
All right, so I just have one question. Yeah, as you said, the behavior, the weak behavior is allowed. Will this project result, or do you think it could result in some sort of a utility to help people test their shaders? Like, for example, if you write a parallel queue, then maybe something that would mangle the sphere V in a way that you could provoke weak behavior by reordering, the stores and the writes between fences or something like that?
Yeah, I mean, that's an interesting question. I think there's different techniques that are out there. They're probably not all in very usable ways or usable formats, I guess. Like, for example, we have our kind of stress testing techniques and stuff, and maybe it'd be nice to be able to release that as like a library or something where people could just kind of run it with their applications and see what happens. There's more complex techniques in academia and probably out in the real world too, where people like control scheduling and stuff and do that kind of like return old values if they can, and really think about how to mess up programs. But that would probably require a lot more like kind of building of tools that don't exist right now for Vulkan and SpearV.
One more?
So I should know, but I don't, about the state of conformance testing of the memory model in Vulkan. Have you had an opportunity? I mean, that code's in open source. Have you, I know we had a hell of a time developing it, and I don't know how good it is. Do you have a view?
I know there's at least 1 or 2 memory model tests in there. Like after that AMD bug was found, that was put into the Vulkan memory model testing. Yeah, into the repository. It's not quite, it doesn't have as much as the web GPU one does that I wrote. And yeah, it's kind of a timing thing and how much, maybe we can get an undergrad at Santa Cruz to work on it. But it'd be nice.
Yeah, I mean, it's where it seems like the sort of thing that you have to test by hammering on the machine. And
Yeah.
and we tend to avoid that in the conformance test because it runs for hours anyway.
Oh yeah. Well, one of the nice things about our tests and one of the like kind of things we had to justify to the web GPU maintainers was that these tests run really fast. And if you look at previous work, they had to run for days at a time almost, but we've shown that within a 30 seconds or so, our tests are pretty good at finding issues if they exist.
Yeah, it's hugely valuable. Thank you.